Hey everyone, welcome to Proof Faculty's first video. Today's first video is going to be about the Moivre's theorem and how we can prove it. So if we wanted to prove the Moivre's theorem, we're going to have to use mathematical induction to prove this. What is mathematical induction, you may ask? Mathematical induction basically involves two main steps. The first step, the basis step, involves proving that the left-hand side of the equation is equal to the right-hand side of the equation for any given value of n, so that you can move on and progress to the second step, which is the inductive step. The inductive step basically assumes that n equals k is true, and hence proves that, or shows that it's also valid for n equals k plus 1, to show that these two equations, or this equation, is equal to each other. So let's start off with our basis stage. For our basis stage, we can plug in any value of n we want. So let's keep it nice and simple and plug in n equals 1. So on our left hand side of this equation, what are we going to have? Plug in n equals 1, and you're going to get theta plus I sine theta, all raised to the power of 1, which evidently enough is just our cos theta plus I sine theta. That's the left hand side of our equation when we plug in n equals 1. So on our right hand side of the equation, if we plug in n equals 1, we basically get r to the power of 1 multiplied by cos 1 theta plus I sine 1 theta, which again is r cos theta plus I sine theta. So now that we have proven the left hand side of this equation is equal to the right hand side, we can move on to our second step, which is our assumption step. So what's our assumption? We need to assume that n equals k is true. For any given value of n, n equals k, it should be true. So if we let n equals k, our original equation now becomes cos theta plus I sine theta, all raised to the k, is equal to r to the k multiplied by cos k theta plus I sine k theta. Simple enough, right? Now we can move to our third step, the inductive step, which is a bit more difficult, but nevertheless, it's still simple. Now, as I previously mentioned, we need to show that n equals k plus 1 holds true if n equals k is true. So let's let n equal k plus 1. So if we plug in n equals k plus 1 to our left hand side of our equation, this is what we get. All to the power of k plus 1. So we can split this up into two different parts using our power rules. So this is the same as saying r to the k, right, multiplied by cos theta plus I sine theta. Or let's remove this for now. It's the same as saying all of this multiplied by k to the power of k, sorry, multiplied by r to the cos theta plus I sine theta, because this is to the power of 1. Multiplying these two will give you that. So now we can move on and say, okay, what is this equivalent to? Under our assumption that we have down here, we've got the same factor here. So we can rewrite that as this. And using that, we can say, hey, r to the k multiplied by cos k theta plus I sine k theta, all multiplied by r cos theta plus I sine theta. All right, so now what do? We can group up our terms, our r terms, group them all together and say r to the k plus 1 over here. And now we've got to multiply out these two brackets. So what I want you to keep in mind here is you've got imaginary terms and real terms. So I'd like you to group them up together and keep your real terms together and your imaginary terms also together. So for our first real terms, it will be cos k theta multiplied by cos theta, which is just cos, let's put this in brackets, k theta multiplied by cos theta. And then for our second real term, we've got I multiplied by I. I squared is just minus 1 because I is just the root of -1. So square that, you get minus 1. So it's just I squared times sine k theta sine theta. So it'll just be minus sine k theta sine theta for our real terms. Now move on to our imaginary terms. Just drop in a plus I, open up a bracket, and multiply out these two. So what we essentially get is cos k theta sine theta. Theta, sorry, it's getting a bit long. Plus, we multiply these two. Now we've got to multiply sine k theta and cos theta. Sine k theta, okay, and then cos theta. And this is what you're left with. So now, what can we do to reduce out this equation? We can use our addition formula that we know from trigonometric identities and reduce this to rk plus 1 to cos k theta plus theta, right? Plus I sine theta, oh sorry, I sine k theta plus theta. This is using trig identities, your addition formulae. If you don't know them, look over them. And yeah, so now what we can do is basically factor out this theta value here. And then we get r to the k plus 1 cos k plus 1 theta plus I sine k plus 1 theta. Now we've got n equals k plus 1 here, and then n equals k plus 1 over here. So essentially what we have done here is proven that it has held true. So now, if n equals k is true, then it has also been shown that n equals k plus 1 is also true. And n equal 1 has also been shown true. And as a result, n is valid for any positive real values or real integers of n. So we can just say for any natural number of n, it is true for positive values, positive integers of n. And that's it. That's what you do. I hope you enjoyed this video. If you've got any questions or any video suggestions, please leave them in the comment section down below. And yeah, hope you enjoyed the video.